Welcome to 26th lecture of video course on tribology. Today's topic is thermohydrodynamic lubrication. As the name indicates, we are going to combine thermal effects with hydrodynamic effects and find out the pressure distribution based on that. In previous lecture, we studied elastrohydrodynamic lubrication, where we combine elastic deformation with hydrodynamic lubrication. And our conclusions were that if we account elastic deformation, then pressure distribution will be, or maximum value of pressure will be lesser compared to if we do not account elastic deformation. The reason was given as the film thickness will increase with elastic deformation. With increase in a film thickness, pressure distribution or the maximum value of pressure will come down, or contacting elements will be slightly more separated, that will reduce the pressure generation. It was also mentioned that it is not a problem. It is not going to reduce the load carrying capacity of the elements. In fact, indirectly it is going to increase the load carrying capacity of tribo elements. And reason was given something like this. He said that if you do not consider elastic deformation, pressure profile will turn out to be like this. It reaches to maximum value and comes down to the 0 value. It is more like parabolic distribution, offset parabolic distribution. Well, if I consider elastic deformation, maximum value of the pressure is reduced, but that reduced maximum pressure value will be at much more angular extent or towards a sliding direction. You can see that this maximum value remains for the greater extent of space variable compared to this. So, elastrohydrodynamic lubrication is important. If we are able to incorporate in any of the design elastic deformation and combine with hydrodynamic lubrication mechanism, that will be optimized tribo pair. Today we are going to discuss about thermal effect. So, question comes, why should we consider the thermal heating? We have been mentioned that wherever there is a full film, there will be some sharing of the liquid, but does it really cause a too much problem? Fluid film lubrication is used to minimize the coefficient of friction, but here we are thinking about even if slight friction is going to affect the performance. To complete that or to add that, we again refer back to our table which was mentioned or which was discussed in previous module on lubrication. This table showed different oil grades. It is a 10 W grade, 20 W grade, SA 30, SA 40, W stands for the winter grade, and this is a multi grade 10 W 30, 10 W 40, 10 W 15. These are the viscosity grade as is given name given by SAE, as the Society of Automotive Engineers. What these two columns are indicating the viscosity, absolute viscosity in millipascal second. This first column says the 40 degree centigrade, second column gives the viscosity at 100 degree centigrade. Of course, the third column, which is only the partially filled, gives some sort of percentage variation or what will be the final viscosity in that case. So, just refer first one is that 32.6 millipascal second is the viscosity of 10 W SA grade oil at 40 degree centigrade. If this temperature is going to the 100 degree centigrade, the viscosity decreases to 5.57, or in other words, viscosity remains only the 17% of the viscosity which was at the 40 degree centigrade. That is a huge change, almost 1/6 reduction. Similarly, with the oil at the 20 W SA grade, viscosity is high, 62.3, while viscosity at 100 degree centigrade is 8.81. The 14 degree reduction, obviously that 86% reduction, and the final viscosity is only 14% of the viscosity at 40 degrees centigrade. Of course, we cannot choose very low viscosity oil because of a number of reasons. We said that load carrying capacity, if we want a more load carrying capacity, we need to choose thicker oil. Or in other words, this oil which having a lesser viscosity can be called a thin oil, and oil which have a high viscosity can be called a thick oil. Thicker oils are required to increase the load carrying capacity of turboprop. As the load increases or velocity comes down, we should choose thicker oil. If sliding velocity increases and load carrying capacity is lower or requirement is lower, we can choose low viscosity oil. That was a conclusion from our previous module on the lubrication when we were discussing about lubricants, different kind of lubricants. Now, if I do a modeling and I say that let us take this as viscosity, input viscosity, because the Reynolds equation which we derive, we assume the viscosity is constant, is not depending on a space variable. With the constant viscosity, then the temperature is not going to be accounted, and whatever the input viscosity will be accounting that, or we will be using that in viscosity. Using this viscosity of 32.6 millipascal second, what we get a pressure profile accounting the elastic deformation in this case, it comes something around 5.8 or 58 megapascal. Now, if I account this viscosity, you see that even the viscosity grade is same. Maybe in one case the turboprop was operating in a 40 degree centigrade, in other case it is operating at a 100 degree centigrade. So, this viscosity should be accounted, that is a 5.57 millipascal second. You can see there is a huge variation or decrease in load carrying capacity or maximum pressure or pressure variation. Here it is a roughly 5.8, while here it is roughly 0.75.8. From 5.8 is coming out to the 0.8, that is huge decrease in maximum pressure value. That means, if temperature is going to change, viscosity as a result will change, and if there is a change in viscosity, load carrying capacity is going to be much lower. Based on this comparison, we can say that there is this load carrying capacity or this pressure distribution variation is just only 14% of this pressure variation. That means 86% is a decrease. Now, viscosity decrease, we say that viscosity 100 degree centigrade was 17%, and if we are using this viscosity, load carrying capacity turned out to be only 14%. Still viscosity in a higher side compared to load carrying capacity, but we can roughly say the load capacity is proportional to viscosity. If there is a reduction in viscosity, load capacity is going to decrease, or there is a more possibility of contact or metal to metal contact. That is a problem. When this kind of the problem comes, then we need to account thermal effects. There is a possibility the temperature rise happens only 2 degree, 5 degree, 10 degree, or if the system design is not good or external temperatures are very high and that are going to increase the temperature of the system, then viscosity thinning will happen, load carrying capacity will decrease, and that may cause the failure of turboprops. So, this is the reason why we should consider thermal heating. We should account thermal effects either coming from outside external sources, generated within the sources, whatever, we should account it. The question comes, how to account these thermal effects? Is there any mean? Yeah, there is a mean, what we call the energy equation. A simple heat transfer equation which we have studied a number of times in fluid mechanics, where we say whatever the energy is generated or passed to the system, it should be convected away, conducted away, or radiated away. So, there should be some thermal equilibrium equation or heat transfer equation, and that can be a combination of number of equations also. As simplified, if I assume there is no radiation effect, what we can say, this is the convective term, conduction term and heat source term. Heat is been added with this term, heat has been conducted away by using this term, heat is convected away by these terms. Now, this is the temperature variation with the time. Generally, we account this when the heat source itself is fluctuating. Sometime it gives a heat of say the 50 watts to the system, sometimes 75 watts, sometimes 25 watts. So, when the phi is going to be changed with the time, naturally there will not be a consistent temperature, there will be continuous variation in temperature, and we should account that. However, if system is steady, heat source remain consistent, whatever the energy is been added, it will be added continuously, it is not been removed, obviously it is not been discontinued, then we can neglect this term. Then these three terms is velocity in tangential direction or sliding direction, velocity in normal direction between the tribopures, whereas velocity in perpendicular direction if I compare or we say relative to the sliding direction. This is the heat conducted in x direction, heat conducted in y direction and z direction. We are assuming the bearings or the tribopures are in x z plane, and the gap between those tribopures is in y direction. So, let us give some sort of expression for the heat source. So, heat source, of course, I should say that this whole equation is the energy per unit volume, and heat source, this term is also the energy per unit volume. This can be given by the shear stress shown or the shear resistance shown by the liquid or the fluid which we are using into velocity gradient. Now, this velocity gradient can be in number, like it can be in a v in a y direction, it can be z direction, but we already have done analysis using hydrodynamic lubrication mechanisms, and we found relevant or more appropriate term is only the velocity in sliding direction. Perpendicular sliding direction, there was no velocity as such in w direction, we assume that w will equal to 0. Now, if I assume second thing that this tau can be given by a Newtonian fluid, something like this. So, eta into tau is equal to eta into velocity gradient which is already present here. So, this source term will turn out to be eta into velocity gradient square. As clearly indicates, if there is a very high velocity in the same gap, the term is going to increase in a square form. There will be more effect. It is not a linear variation, it is parabolic variation, or there is a square form coming over here. Now, if we give a nomenclature to this symbols, we say that this is the density, that means density is going to play a role. Lubricant density, which is in a kilogram per meter cube. This is a specific heat of the lubricant, I am emphasizing it is of the lubricant, expressed in the joule per unit kilogram and Kelvin. Now, if I multiply density with Cp, what I am going to get is the joule, kilogram will be cancelled, joule per unit meter cube per unit Kelvin, and here that is everywhere Kelvin coming. So, that can be cancelled out, and in this situation is per unit time, this is also per unit time because the meter per unit second, per meter per second, and meter will be cancelled out. So, it will turn out to be per unit second. This also per unit second, obviously the Kelvin per unit second, and all the four terms will be in Kelvin per unit second, and this is the joule per unit second, turn out to be watt, and what we say that overall this expression will turn out to be watt per unit meter cube. That is why I say this whole expression has been expressed in terms of watt per unit volume. We should not confuse with the units, get confused with the unit. Now, interesting thing is that this K is a thermal conductivity of another tribopius. Often it has been mistaken. When we are using conduction term, K comes as a thermal conductivity of the material 1, thermal conductivity of material 2. No. In this situation, we are not accounting the material conductivity. We are still in fluid film zone, in that zone only. So, this thermal conductivity of the lubricant will not be as high as solids, but we need to account. Wherever there is a small gap, this overall conduction will be dominating compared to the long gap. Or another word, we can say, if this is a gap direction, why is it gap direction? Where the film thickness happens in microns, while in sliding direction x happens to be in mm, and z also happen to be in mm, or the dimension in mm. So, dimension in mm, dimension in mm, and dimension in microns. Naturally, this conduction term will be much more dominating compared to this conduction term, compared to this conduction term. We need to keep this in mind. Similarly, in this case, there is a tangential velocity. So, this term will dominate. There is a possibility of the turbulence. There is a possibility of some velocity along the y direction, the lower gap, but that may not be as high as this term. So, many times we can neglect for the simplification. And if there is no tangent and there is no velocity in z direction of the tribopure or not sliding in particularly in that direction, is only the unidirectional, which we know that sliding happens in the u direction only, then this term also will be neglected, right. So, we can simplify this thermal effect, or we say that this energy equation to account the thermal effects with hydrodynamic lubrication mechanism. Now, what is being done over here? We say that we are using only one energy equation. We know there will be heat generation, and that heat will be conducted to the surfaces or tribopures, and there the thickness of the tribopure and thermal conductivity of the tribopure will be accounted. But for time being, we have neglected those aspects, because that is going to give a second equation. We already have one equation related to pressure, that is a Reynolds equation. Then we have elastic equation related to hydrodynamic lubrication mechanisms. Then we have third equation of energy like this, and if we add fourth equation, that will be a too much, or we say that particularly the elementary level courses, it will take a much longer time to understand, and it can be done at only the research levels, and when we have very good high computational facilities, even on those computers, this overall equation will take a days to get any answer. It will not give results in seconds, not minutes, not hours. It is going to take much longer time. That is why we are for time being neglecting it. But whenever the situation comes, we say there is a thermal heating outside the tribopure and we need to account it. Let us take an example of IC engine. With IC engine, outside temperature is very high and maybe tribopure does not come to that high temperature, then we need to account this temperature. Or if there is a forced cooling, there is a water circulation system going around tribopures, then we should account those things. But to generalize, to include over here, it will be difficult. Whenever the situation comes, wherever the application comes, we will account this. Now, the time to simplify energy equation, as I say that we are not considering the second energy equation or second heat transfer equation, we are still on the simplified energy equation, and we want to further simplify it. So, we want to neglect this term. It is the transient solution, we do not want to go ahead with that, we want to go for a simple solution. Now, this term is neglected in this case. The second simplification will be, now I will account only the tangential velocity along the x axis, we are not going to account any other thing. So, these two terms also will be cancelled. or will be neglected. Simple. So, from so many terms we have reduced one term here. Now, we have further reduced two terms. So, there are three differential terms have been neglected, and we know there is a gap or the film thickness happens in this gap, and we are assuming that this surface is sliding, this surface is stationary, and this film thickness is in microns, while this sliding distance is in mm. So, conduction is predominant only in y direction. So, what I am saying that the arrow, this is a y direction, this is x direction, and perpendicular to the monitor, perpendicular to the our configuration, that is a z direction. So, variation or conduction in z direction is negligible, conduction in sliding direction is negligible compared to conduction in film thickness direction. So, we will consider only this effect. Of course, this has been simplified earlier. We said that we are using Newtonian liquid, we are not using non-Newtonian liquid, and we know very well that most of the liquids are non-Newtonian liquids. If we introduce non-Newtonian liquid over here, that it is going to increase the complexity. So, it is always preferable to think simplification first, get a feel, get a impression how these equations are going to work, get a confidence on that, and subsequent we can improve or we can incorporate the slightly more complexity in that. So, the simplified energy equation, say convection in sliding direction, conduction along the film thickness direction, heat generation along the film thickness direction. Now, what are the difficulties? I have already simplified so much, and still I am saying that there will be some difficulties. I want to elaborate that. I want to just discuss with you. Is it really so simple as a aerodynamic lubrication? Is it so simple as elastoaerodynamic lubrication? I have seen a number of articles. People feel that elastic deformation or counting aerodynamic lubrication is much more complex compared to incorporating thermal effects. But in my view, accounting thermal effect is much more laborious, involves much more labor compared to elastic deformation, compared to pressure distribution using Reynolds equation, and that is why I want to just mention over here. In this case, first thing is that how to find out thermal conductivity of the liquid. We know liquid is subjected to the pressure, molecules will be closer, heat conduction should increase. Now, if there is some sort of a streamer formation, there are some air bubbles in the liquid, and that happen to be in a divergent domain, what will happen? Thermal conductivity of the liquid will come down, will reduce. So, thermal conductivity of the liquid cannot be consistent, but how to account that is pretty difficult. Number of models are there, people have suggested, researchers have suggested. For time being, we have to assume this K is constant, it is not going to vary, because in this case we are not introducing the pressure immediately. Of course, it will be done iteratively in a sequential manner, but it is not directly. If we say that K is going to depend on the pressure and we are to incorporate it, is again going to be very long, lengthy work or the laborious work. So, for time being we are assuming K is constant. So, that is the first difficulty, unjustifiable assumption. Now, what is the second thing? It says that how, from where you bring this u. There is variation or there is a velocity of liquid. It is not a velocity of sliding surface. We know velocity of the sliding surface will be constant over here. Maybe say in this case u is 0. In this case u is capital U. Fix, easy. We can account that way. But to account the fluid viscosity, we need expression. First thing comes in our mind, oh, we have already done this in the aerodynamic lubrication. So, where is the problem? I can use this equation as it is. We have done this, we have derived this equation, Reynolds equation, when we driving the Reynolds equation, we consider one surface as the velocity u1, other surface the velocity u2, and overall velocity profile can be given like this. That is right, but the problem is that we assumed for that derivation the viscosity is constant, it is not dependent on any space variable. Well, here we are not doing that. We are saying the viscosity is going to vary with a space variable. It will vary along the x axis, it is going to vary along the y axis also. And of course, if you consider third dimension, it is going to vary along the z axis also. So, how can we justify this velocity? It is not possible. That means, if we incorporate this relation as it is, we are doing something wrong. We are not moving to the right direction. Our assumptions are absolutely wrong. We cannot use this kind of velocity profile in this. And there is another difficulty. So, how do we incorporate this viscosity? You know, viscosity is a strong function of temperature. You can we are able to see the eta over here, we are able to see eta over here, and this is the source term. We substitute this eta over here. You say that initial viscosity is known to us, initial temperature is known to us. This beta, which is a material property, or in this case a particularly oil property, is known to us, but still T is here. T is going to be here. T is in a differential form, so it is going to give us a overall complicated equation. There is a e, there is an exponential term here. Integration will not be that simple, and that is going to introduce difficulty. So, what we are getting? Difficulties are the energy level equation. We are not consider variation along the z direction. That is the first difficulty, because if we incorporate that, that is going to increase our efforts. Second, we do not know how to incorporate velocity, and whole energy equation is going to be dependent on that. If velocity expression is wrong, whole equation will turn out to be wrong. Next one is our viscosity. How to incorporate this viscosity? By using this and integrating an exponential term when we have a second order equation. So, these are some difficulties. In addition, there are difficulties of the boundary condition. See, this is the partial differential equation with the variation along the x axis, variation along the y axis, and we require at least two boundary conditions to solve it. And what is the first boundary condition? We say first boundary condition may be easy. Why no? Very well. What will be the temperature at the entrance? Because we are going to supply this lubricant. So, we can say the entrance temperature is T in. This is in Kelvin, that is why the capital T. But the problem comes. We have studied hydrodynamic lubrication. We said there will be a pressure retardation, there will be backflow at the entrance, and whatever the liquid over here, it has a high temperature, is going to get mixed with the entrance liquid. Even though I know what will be the supply temperature, but not necessary at the entrance of this zone, this will remain T in. It may be higher than T in, and which we do not know. We need to know how much lubricant is recirculated, there is the backflow of the lubricant, and how it is going to get mixed with a fresh oil, because fresh oil is not 100%, it is only the partly fresh oil will come and partly backflow will be there. So, they will get mixed, and this temperature condition, it's again is a problematic. We cannot use this as it is. We require rigorous analysis to find out what will be the temperature at the entrance, and I am sure it is not going to be T in, it is not going to be supply temperature. What will be the temperature at the exit? It is not known at all, it cannot be predicted. Everything, the whole heat generation is going to happen over here, or maybe some heat generation is happening outside also, we need to account that. So, defining exit boundary condition is also difficult. What is the easiest one? Easiest, we say that there will not be any variation at exit. Whatever the temperature is going to be here, maybe more or less same temperature will be outside, assuming there is no cooling outside. And maybe temperature reaches to one high level and after that is coming to the open air, it will not cool down immediately. So, there will not be much variation in temperature. Whatever the one node before that, the same temperature should be there, which is again wrong. We know there will be some cooling, but how to account that cooling? It is not known. We are simplifying, we are using very simple assumptions, right. So, these are the two most commonly used boundary condition, but there is no definite logic behind this. There are a number of assumptions and assumptions are often wrong. There are other difficulties also, and of course, this is what already I mentioned, the mixing of lubricant. There will be lubricant supply and there will be backflow and there will be some mixing of that, and then after mixing the temperature at the entrance will be different, but we need to account that flow, backflow conditions. This is another difficulty, meshing. What we done in a hydrodynamic lubrication, we did meshing in x direction and z direction, and we kept del x is equal to del z, or del x bar is equal to del x z bar. We try to keep the same spacing, but you can see here there is a convergent, there is a continuous reduction in spacing available to us, and we cannot say there will be, let us have a 6 nodes here and I will have a 4 nodes here and a 2 nodes over here. That will make a lot of difficulty for the finite difference method. Other one is that let us say that all the number of nodes are same at this junction, this junction, this junction, almost every junction number of nodes are same. If I do that, what is going to happen? This spacing is continuously decreasing, and that is happening with the slope. It is nothing like I take some absolute value and then some definite decrement. This is the decrement going to happen with the slope. Everywhere spacing is going to change, and in computer program we need to account that. At every node spacing is going to change, and it is very difficult to find out element as such an area unless we do some approximation. In other words, this was a much more simpler situation. What we did with hydrodynamic lubrication, x direction, z direction equally divide, rectangular mesh, no problem, we can account it. Because for simplification we say that del x bar is equal to del x z bar, there was not much problem, while here the problems are. We have to account this, we need to account this in computer program, and inaccuracy will also change. Of course, one justification can come that towards a decreasing direction temperature is going to be more, so spacing should be lesser. From that point of view, it is justifiable from accuracy point of view, but kind of the degree of difficulty which is getting in is on a higher side, and we need to do a proper programming for this purpose. There are other difficulties, what we call a directionality. Computer program does not know whether which side temperature is going to be in a higher side, and is the numerical iterations. Anytime one iteration goes wrong, whole solution turn out to be wrong. That means we need to give some directionality. We need to tell computer program, yeah, as we are moving towards x direction, there will be increase in a temperature. Our easiest way is that you divide in a zone. Say there is a north zone, there is a south zone, there is a west zone, there is a east zone. On east side there is a slope and there is a convergent. That means whenever the temperature has been calculated, it should be compared between the east and west. Say east need to be higher than the west. So that kind of directionality is important. But many times we say that if the external environment conditions are going to change, if there is external cooling, this kind of temperature profile may not be same, because we are forcing the solution, we are not allowing it to naturally grow, and this forcing is essential for our purpose. Otherwise we will not be able to get definite solution. If I do 10 different iterations, I may get 10 different results unless we do forcing. But when we do forcing, we give a direction, we are going to face problem. Or we say that we will not be able to accommodate outside boundary conditions. Everything need to be known to us, and if everything is known to us, then we don't have to do any simulation. Why do we do simulation when everything is known to us? Sometimes people or sometimes researchers suggest you do experiments as well as theoretical calculation. Few observation from experiments, substitute those observation and then do modification. That is the best approach. Of course, we need to do simulation as well as the experimental, because we know the experimentation on all the parameters is very difficult. Whichever parameters can be measured easily, we should use experiments on that, and remaining parameter can be calculated based on theoretical calculations. So, absolute sense, theoretical calculation are not going to give 100% correct results, because physics is not completely known. There are, if you see that if still the physics is known, computational difficulties will give different results, may not give accurate results the way we want. So, there are number of difficulties, and this is what I mentioned that the way we have done a pressure expression P I plus 1, P I minus 1, P I j plus 1, j minus 1, same way the temperature has been calculated in a similar term, and this E term sometime turn out to be negative, sometime a positive, depends on external environment, and this need to be checked. It should not be going in reverse direction. Now, we are coming to the how to account velocity. As I say earlier, velocity of the liquid is need to be right. If we are not able to calculate, evaluate or estimate velocity of the fluid properly, then whole energy equation will turn out to be useless. To develop the expression for the velocity, let us start again with hydrodynamic lubrication equations. You say take an element, we use a force balance equation. I hope you remember this expression. This is a very simple expression. We say we are using Newtonian liquid, and there is a gradient of shear stress, and that is equivalent to the gradient of pressure. In x direction, similar kind of expression will come for the z direction also, but in this case we are more focused only on one dimensional case. If you are happy with the one dimensional, then we should switch to the two dimensional, but I am sure once you see all the equation with for the one dimensional, you will not think about the second dimension at all. Now, this is simple, integration is simple. So, okay, integrate, we know the dp by dx is not going to depend on the y, that is an assumption. If you remember in previous slide, we have assumed the pressure variation only in x direction and z direction, but temperature variation in y direction. Okay, this is a y, this is a x, and that is a problem. We are assuming the whole y direction, the pressure is constant, but in y direction temperature is going to vary. So, there is a lot of difficulty in compatibility. One variable is not changing at all, other variable is changing only in that direction. Now, so this is the integration. Simple say that once you integrate, we will get integration constant. As we know, the eta is depending on the space variable, we divide here and we try to integrate here. Now, in earlier case what we did, we simply took this eta out, and then we integrated y dy as a y square by 2, substitute the value of y as a h, and we got the simple expression. But here eta is depending on the y, and we do not know what is that, because it has to come through the temperature, it has to come directly from a simultaneous solution of two equations. So, for time being we do not know how eta is going to vary with y. So, this is integration which is not known to us. Similarly, in this case also eta is depending on the y, so we cannot integrate easily unless we have this definite relation, and this is the second integration constant. And there are two integration constants C1 and C2. What we need to do? We need to use two velocity conditions. For simplification, we assume that lower surface has a velocity u and upper surface velocity is 0. Just keep in mind, In earlier case we kept both the velocity u1 and u2, but we want to simplify this expression. That is why we are assuming one surface is a stationary, it is not going to move, it is not moving. That is why velocity is 0, and when velocity is 0, calculating the expression for the integrations or the integration constant will be much simpler. So, simplify that, we are using this boundary condition. Now, we have these two boundary condition, substitute, get the results with the C2 is a capital U2 and C1 will turn out to be a expression, in terms of pressure variation, in terms of viscosity variation, where the viscosity variation is not known to us. We do not have any relation for time being. If we have a relation, we can substitute, we can integrate it, but otherwise we have a problem. Now, we have two integration constant, we can substitute, we can find out the expression for u, and we can use a continuity equation. As we have done in hydrodynamic lubrication, we merged force equation with the continuity equation. So, same thing we are doing here. We have earlier in previous slide we solved for the force equation, now we are solving it for the continuity equation. On a simpler side, we assume these two terms are negligible, otherwise expression will be much lengthier, much more complex to understand. So, simpler one, say okay, this term is negligible, this term is negligible for time being, and more or less if the W is not active, or we say that there is no velocity in perpendicular to the sliding direction, then this term will be negligible, and there is no squeezing action, there is no turbulence in that, so this velocity also will be 0, this is not going to change. So, this is only one term. Now, to utilize this, we will be using this u as this has been expression which we have derived, and C1 and C2 constants were derived in previous slide. So, we are using those things. Now, to be on the simpler side, to simplify this expression, what we are doing, we are keeping we are separating u term and dp by dx term. Say dp by dx into some multiplication factor, velocity u and some multiplication factor n. So, m and n can be figured out by using this rearrangement of the equation. If I do rearrangement, what I am going to get, m is equal to this first integration, second integration, third integration, fourth integration, and this is a term which we need to solve to get velocity profile. Similarly, n also can be figured out by rearrangement. There is a one integration, the second integration, of course, we are using integration limits 0 to h, in other case is the floating one, the 0 to y, and y can vary from 0 to h depending on the which node we are using. So, these are the not as simple terms. If we have a definite relation for eta in terms of y, then these terms will be simple, but we do not have any such relation available to us. That is why these terms will be slightly difficult to account this kind of terms. Now, we have done like this. Now, we need to integrate and then differentiate. Integration will not be difficult. The way we have done this, we have simply arranged in a nice manner. So, now simply what we will do, the integrate this term whole. This will be having two terms, dp by dx. So, this integration should come over here 0 to h, and dp by dx m dy. Second term will be u and dy. Now, if I do this integration term by parts, what I will get, I will get two terms. In first case, it will be there. In this case, differentiation is also there. So, what we are going to get, first term as a differentiation or second derivation of the pressure and integration of m over the y, and the second term dp by dx will be as it is, while this will be the differentiation term and integration term. As we do not have integration, we cannot differentiate also. Similarly, this term u, the differentiation of n dy, the integration of this. As we do not have this integration values available to us, we cannot differentiate easily. So, the whole thing is focus on what is the relation of viscosity with a y, and we do not have any relations. It has to be represented in the time, or it has to be represented in the temperature. Once we represent the temperature, That means this equation and temperature equation or energy equation should be simultaneously solved, which is a complex term. It requires a many iteration to come to the right solution. Number of examples we can do also this. We can integrate and we can substitute what we call as the thermohydrodynamic lubrication mechanisms, and I have a couple of cases available which shows that how to crack this problem. So, I am going to show the 3 examples. So, real data available and results obtained for these 3 examples. Say we are taking example of journal bearing. What is the journal bearing, how it works, we are going to discuss that in the next module on application side. But just for the completeness, I have shown this diagram. Let's assume there is a shaft and this is a bearing, and shaft has a radius R2 and the bearing has a radius R1, and they have some clearance. Obviously, the R1 is greater than R2, and this clearance is need to be what we represent as the C, and here the value is given R by C. The radius either of the shaft or the bearing, they do not have much difference, it is in micron difference. This ratio is 637, that is the ratio given to us, and length is defined, the length of the bearing, which we have I have shown on this case is the cross section, and assume that perpendicular to that will be length. The length is given as 70 mm, and this length by diameter ratio is given, that we say that this is a 0.7. As the length is already known, I will be able to find out what will be the diameter, right. So, diameter is known to me. Once the diameter is known, I will be knowing what is the radius. Once I know the radius, I can find out the C. Here this is omega, that is angular velocity of the shaft. I mean, we are assuming the shaft is sliding or is rotating about its own axis, and there is a sliding velocity. And this is the constant B, which is generally given for the velocity or viscosity related relation. This is the rho and C is rho 0 and C 0 equal to some value which has been given for liquid. This is the applied load. We are assuming that applied load on the bearing is a 3920 is the input temperature with the supply temperature or lubricant was supplied. This is the viscosity or eta n, that is given as a 19.2 millipascal second. However, there is an additional term what we call a supply pressure. In this liquid is being supplied with some pressure to the force feeding. There is a some groove to pass a liquid from one place to other place. We will discuss all this, and when we discuss about the detail or we say the application of journal bearing and how to design the journal bearing using our topological knowledge. And we have 10 degree like circumferential extent and 60 mm is the length. So, what is the purpose of giving this example? We say that need to be done with some experiment and more theoretical calculations. So, some experimental data are available. We say the applied load is 3920 Newton and maximum temperature on the surface which was measured was something like a 56 degrees centigrade. Input temperature is a 40 degree and maximum temperature 56 degree. That means there is 16 degree temperature rise, and sometimes 16% temperature rise can reduce the viscosity by 30 to 40%, and that can reduce the load carrying capacity or the parameters. However, this is one of the very lightly loaded bearing that is coming that can be judged from this eccentricity value. So, eccentricity value lesser than 0.5 is known to be a lightly loaded bearings, and we are able to see when we are doing a TSD analysis. T is thermo, H is hydrodynamic, and D is a thermohydrodynamic lubrication. Yeah, H is hydro and is a dynamic. So, thermohydrodynamic lubrication. Here we are using a boundary condition. We are using the isothermal and adiabatic condition, which the rotating element is not going to vary the temperature, because there is a high convective term in that. So, that will remain the same as a constant temperature, that is isothermal temperature. While stationary surface is not going to conduct any energy to other surface. So, that is the adiabatic surface. So, here the boundary condition has changed. We are using iso-adi solution. This expression is so that we can use the same expression as a hydrodynamic lubrication mechanism expressions or the pressure expressions. What we need to do, we need to find out one effective temperature, and that effective temperature has been estimated as a 51.38 degrees centigrade. This can be done by measuring the liquid which is coming out of the bearing. When general bearing is used, there will be leakage of the liquid or leakage of the lubricant. We can collect that lubricant, we can measure the temperature, and that measured temperature is a 51.38 degrees centigrade. That is what we call as the effective temperature which is coming out of the bearing, and performance is based on that. And this is a solution based on the hydrodynamic lubrication and iteration, and effective temperature has been measured by after the iterations. So, there I am showing the 4 results. One is the TSD result, thermo-hydrodynamic lubrication. It should show the very good results because it is going to take more than 100,000 times the time compared to what these solutions are taking. I am just talking the 100,000 times solution time. It takes hours to give the results. Now, this P applied load in all the cases is the same because whatever the experimental measure, we are giving this as an input. What we are going to get a maximum temperature, this experimental result is 56. When we are using a TSD analysis, what we are getting a 54.18 degrees centigrade. That is lower than what experimental measure temperature. But we know very well thermocouple which we use, it has generally a inaccuracy of plus minus 1 degree. So, this much difference is not a very critical or crucial. However, coming to the this boundary condition, this isothermal and adiabatic boundary condition, this is able to give a 57 degree centigrade. It is not too far from a TSD, and this takes much lesser time compared to TSD solution. Now, this is cannot give the maximum temperature because it is based on simple temperature collected at the exit of the bearing. Well, in this case, what we say the effective temperature and doing the iterations is more like a ISO ADI, but it gives slightly better results because of the iterations. It takes slightly more time compared to this solution, and it gives around 58 degrees centigrade. So, there are two extremes, a 54 measured at 56, and this gives a 58, and there are other parameters. Now, what is to be important to be noted over here is the Q recirculation. In all the lubrication algorithms, it has been calculated, the recirculation of the flow has been calculated. It is nothing like the whole liquid is moving out, is being leaking out. Partly the liquid is again entering back, and that is why the inlet temperature of the temperature at the entrance will be a mixture of the temperature which we are supplying, or liquid we are supplying the some temperature plus this recirculated temperature. That means the algorithm need to incorporate those. You can see here the Q recirculation in all the cases. In this case particularly is a 19.5 units. ISO ADI is 18.81, 18.72, in this case 19.24. In all algorithm recirculation has been accounted, and this you can consider the factor the leakage. Leakage here is a 29.16, slightly more than what is been circulated. Same thing over here, same thing, and this one. So, we need to account the flow condition in this case, and when we drive the hydrodynamic condition or elastohydrodynamic lubrication or thermo-hydrodynamic lubrication, we are not accounted this recirculation liquids, or it's a liquid which is getting recirculated. We should account that. However, developing expression or general expression for all those conditions is not possible. That is why we take specified application, or we solve all this by application point of view. We can take a roller bearing as an application, cam follower as an application, gears as an application, general bearing as an application, and then we apply these algorithms. We know most of the situations will be simplified, not necessarily the gear pair will show the similar behavior, the roller bearing will show the same behavior as the general bearing. So, this will be having very specific equations which obviously that some assumption which are specific to the applications, and solution will not be that difficult as it appears in absolute sense. We will be discussing that kind of solutions, or we can say that our next module will be on the application, whatever we have learned in our fundamentals of the friction, fundamentals of wear, fundamentals of lubricant and fundamentals of lubrication mechanisms, or Reynolds equation or elastic equations, we will be utilizing those on the application side, and maybe we will be able to give better results or with better understanding when we apply it. Thank you. We will continue this module next time. Not in this module, we will be considering the application. Of course, as I mentioned, we have 3 examples. I showed only one example. I do not have much time, but I can quickly refer to the second and third example, and these are more or less same, consistent. But this example says that only the geometry parameters have been changed, load has been changed, axial groove arrangement has been changed. Now, you can see here the initially the eccentricity was lesser than 0.5, while in this case eccentricity is slightly increasing, it is coming to the slightly moderate loads, and we are able to see the temperature, the T maximum experimentally measured temperature is 49, while TSD solution also gives a 49, while this approach which use effective temperature calculation gives a temperature of 49.64. There is another parameter which has been measured and been quoted as a P maximum, that is a 1.3 megapascal pressure was the maximum pressure calculated or measured, and TSD gives a 1.25, which is slightly difficult to understand. Unless the pressure is right, it should not give the good results. However, it has been shown the 1.25, 1.25, 1.25. So, either there is some sort of inaccuracy in measurement. All the solutions are showing the lower pressure, lower maximum pressure, or maybe there is some inaccuracy in calculating the maximum pressure. Similarly, there is a third solution, the third example, more or less again the same data. The load has been increased to the 6000 from the 4000, and there are some change in the input parameters. What we are going to get here, the P maximum experimentally measured is a 1.9, TSD gives a 1.78, and this approach gives a 1.8. So, again maximum pressure is on a slightly lower side compared to experiment measured, and temperature which is measured is coming to very close. Here the maximum temperature which is measured to the 58 degree centigrade, TSD estimates around 58.35 degree, while this approach which requires effective temperature and some iteration gives a 57.15 degree. So, not a huge variation as such in this case. Results are more or less same, while in this case the Q leakage has been also measured, is a 130.6, and we are able to see that more or less same Q is been estimated by number of analysis. Or in a short, I can say that thermohydrodynamic lubrication is generally a specific application, or there is need to be specific to application. Whatever the equations we solve should not overburden our computer program, but after understanding the application we can simplify those equations and then we can get a good solution. And we need to know the boundary condition properly. Many times the boundary condition can be used by experimentally measured data that will give a good estimation. As far as possible, we should account elastic deformation, because that is going to give a lesser pressure, the way we have seen in the previous slides. Maximum pressure value was lower, and we have considered only the dissipation within the liquid, and we are not considered heat transfer within a solid surface. As far as possible, if the situation permits us, we should account that. Or in short, it is slightly on the high side to think that we should get a complete TSD solution which involves a thermal, elastic and hydrodynamic lubrication mechanism. But if application is like that, like a gear application, where we need to account all these factors to estimate the right load carrying capacity. If we do not account all properly, there is a possibility of the wrong estimation, and which will not give us good results. So, it depends exclusively on application, which kind of equations are going to be properly fitted in that application. But we cannot generalize, we cannot use all the equation and try to get a solution. That will take much longer time and may not give much more fruitful results to us. Thank you. Thanks for your attention. We'll consider or we'll discuss application oriented model next lecture onward.